Okay, so before each topic, I would like to do some recall, okay? Especially today's topic is DC-DC converter, okay? So actually, topic 1 and 2 correlate with the DC-DC converter topics, okay? So I don't know if you still remember, okay? So at the very beginning, we have this kind of converter, right? Actually, at that time, we don't know it is a converter. Okay, we just know that the technique here, just like a switch mode conversion, right? So there is a bidirectional switch, up and down, and then there will be a resultant waveform like this. Okay, and this is a physical switch. But in topic 1, we know that some applications or most applications of power electronics interface um, needs high frequency, right? So this kind of physical switch cannot suffer. So that's why we have this kind of topology. So here there is a combination of the transistor and diode. So this connection can act as an electronic switch. Okay, it can goes up with very high frequency, uh, up to kilohertz or even megahertz. Okay, and then in topic 2, we learned transistors and diodes, right? Why? It is because the electronic switch is made of a combination of transistors and diode, right? So those two components are very, very important in that kind of converter. Okay, so here in topic 2, we mainly go through MOSFET, IGBT, and BJT, right? And then later in the second half of the subject, you will also learn SCR, the varistor converter. And actually in the simulation lab, you will also um, work with this kind of converter. Okay. And then for the diode, it can also be classified into many types in terms of switching frequency and voltage drop. Okay, so you can select the diode mainly uh, from those two factors. Okay, and then MOSFET is very one. In the applications, it is because if you still can remember that picture, so the operation frequency of the MOSFET is the highest, right? However, its power capability is the lowest, especially when compared to the SCR. Okay, and so we learned the details for how to operate MOSFETs in the converter. Okay, and in general, MOSFETs for its operation region can be classified into three regions. Okay, so uh, for the power electronics interface, we only use the first two regions. Okay, first two, and then how to determine what is happening, okay, during the regions. So you just need to look at VGS, right? VGS. So when the VGS is below the threshold, nothing happened, right? So the MOSFET is off, okay? And then when the VGS is higher than the threshold, there will be the drain current, right, from the drain to the source, okay? And at that time, the drain current will be proportional to the VGS, okay? And then if you want the MOSFET to carry a certain level of the drain current, you need to apply a certain level of the VGS. Okay, so that is the very general operation regions of MOSFET. Okay, so later we also learn how what happened. Okay, when we turn on or turn off the MOSFET in the converter. Okay, so here is the MOSFET, and then here is the diode. And for this topology, the special thing is there is a constant current source in the low side, okay, in the low side. So it means that if this transistor is off, there will be still a current fuels through the diode. Okay, so later, especially in the second half of the subject, you need to pay attention on the loading. Okay, so sometimes it is open, sometimes it is with a constant current source, and sometimes it's with a resistor. Okay, and so on. Yeah, so you just need to read the topology very carefully. Okay, and then this is the turn-on characteristics waveform for VGS, drain current, and VDS. Okay, so actually these waveforms you don't need to just memorize the shape. It is because the shape is very simple. Okay, but all you need to know is what happens at the specific time slot, right? So those time slot actually depends on what I just mentioned on the VGS. Okay, so two specific points or critical points. Okay, so one of them is the threshold level, and the other one is the specific level of the current that you want the MOSFET to carry. Okay. Okay, and after turn on, we have the turn off characteristic. Actually, all the things the other way around. Okay. And then after that, we also learned how to calculate the power loss of the converter. Okay, so in the converter, two main components, right? So transistor, and here the MOSFET is the example, and then the other component is diode. Okay, so actually we just consider the power losses from those two components. Okay, so this is a brief summary. So we have the conduction loss for MOSFET, switching losses for MOSFET, and then for diodes, there are the other two types of losses, forward loss and switching loss. Okay, and those equations, it is because in this semester we will have the online exam, right? And it is open book, and so you don't need to. Yeah, it is because in the past we don't give this kind of formula list. Okay, so some students need to memorize the equation. Actually, you don't need to uh, just memorize. There should be some methods. Actually, I also mentioned in the lecture. Okay, for you to understand how come the equations. Okay, but if the exam is online with open book format, you don't need to memorize. You can just copy. Okay, and use the equations directly with the given parameters. Okay. Okay, and so here, just for your information, so up to now, you can see that there are many subscripts, right? So many subscripts. Okay, so each subscript has its meaning. Okay, so here is a I cannot say that it is a unique meaning. Okay, uh, here is just a generic use of those subscripts. So for example, M stands for maximum or peak. Okay, and then F stands for forward. Okay, it is because, for example, here we have V with the subscript F and M, right? Okay, so actually this one is the maximum forward voltage. Of course, now we are talking about the loss. So this is the maximum forward voltage drop of the diode. Okay, so yeah, so you may need to know the meaning of those subscripts. Okay. Okay, so topic 3, buck converter. So from this topic, we will really draw some waveforms as our results. Okay, so please do some practice. Okay, after this topic. And first of all, I here just want to introduce you the concept of DC steady state. I think you may know this term, right? From level 2 electronic subject. Okay, but here just want to refresh your memory. Why it is because in this subject, all DC-DC converter are considered in DC steady state. Okay, so at the very beginning, you need to make sure you know the concept of DC steady state. Okay, okay, so so actually DC steady state is an equilibrium condition. Okay, so what is the equilibrium condition? So it means that the beginning or the initial condition is equal to the final condition, right? There's no change. There's no change. So you will know more in this slide. Okay. So here, so for this one, the initial point is here, and then the final point is here. So you can see that there is an obvious increment for current. Okay. So for this one, the condition is transient. But now we just consider the converter in DC steady state. Okay, so it should look like this. Okay, so here the initial point is this level, and then the final point is here. Okay, so it is a steady. So it can also work for the voltage waveform. Okay, so the magnitude is the same, 100. Okay, so for each cycle, the peak value here is still 100 volt. So in the sentence, DC steady state means all the waveforms repeat exactly every switching period. Okay, so obviously here, okay, so obviously here is one cycle, right? And then this is the other one. Okay, and do you still remember TS? Do you still remember? Okay, so TS stands for switching period. Okay, so this is the other switching period. Okay, so for each switching period, all the waveforms are identical. Okay, they are identical. Okay, okay, so this is the summary actually. Okay, so initial state is equal to final state. Okay, they are identical. Okay, so you should not find that fundamental increases against time, and also you don't find the switching time changing against time. Okay, so all the things are constant. Okay, all the things are constant. So that is the concept of DC steady state. Okay, and there is a summary or a comparison between non-switching circuits and switching circuits. And for power electronics interface, we consider circuits as switching, of course, right? Okay, so if you don't want to know what happened for the non-switching circuits, you may just pay attention on this. And here I highlight two sentences that is very important. It can help you to resolve the problems about the DC-DC converter. For example, it may also help you to draw the waveforms. Okay, so here, the first one, the average voltage across an inductor is 0. Okay, so in symbol, inductor voltage is equal to 0. Okay, and this is average. So in topic 2, I also mentioned there are two types of parameters. right? So this is the small letter, and this is the capital letter. So capital letter means constant, right? This is a constant value, and the small letter is a variable. It will change against time. Okay? It will change against time. So this is a constant. So actually here, this one here. So uh, this is small letter voltage. It is because it can change against time, right? And then this is the average. This is the average. So sometimes we will use this one. Okay, so we can see that there is a bar on top of the symbol. It is a average value. Okay, you can see that in the topic of motor drives. Okay, so in that topic, there you can see that there is a bar on top of the parameter, and it means that value is a constant value. Okay, or now here in the DC-DC converter topic, so you can use this. Okay, capital letter V with the subscript A. Okay, and A here stands for the identity of the switching power pole. Okay, it is because there should be many or more than one switching power pole in the converter. Okay, okay, so this is again a recall. Okay, so this is the capital letter V. This is because this is the average voltage, and L stands for inductor is equal to 0. Okay, so that is a must. Okay, in a switching circuit. Okay, and then the second statement, average current across its capacitor is 0. Okay, so average current. So we need to use the capital I, and then capital C for capacitor is equal to 0. Okay, so at this moment, you just need to remember these two statements, and later you'll know how we can use uh, those for our waveforms or calculations. Okay? And here's a recall. I think you should learn it in level 2 subjects. Okay, so that is the beauty for using the DC steady state to analyze the circuit. It is because, for example, this kind of very complicated circuit, we just consider this circuit at DC steady state. It can be simplified like this, right? So why? It is because at this DC steady state, the capacitor is just like open. Okay, yeah. So and then the inductor, we consider it just like short. So at the end, we'll have this very simple circuit. So that is the beauty for using the DC steady state to analyze the circuit. But why we need DC steady state analysis? So these are the advantages. Okay, these are the advantages. I don't want to spend time here. You should have learned it before. Okay, and more information for DC-DC converter. So DC-DC converter, right? So the source should be DC, and then the load is also DC. And the power flow should be in only one direction, in one direction. I mentioned in topic 1, some of the converters can have bidirectional power flow. Okay, no worry, you will learn it in the second half of the subject. Okay. And it is because here the power flow is only in one direction, so both voltage and current remain uh, unipolar, and also unidirectional. Okay? And this is a, I think we saw it before, right, in topic 1, am I right? Okay, so again, this is a DC-DC converter, and then input voltage is DC and output voltage is DC as well. Okay, and then there should be a monitoring or a sensing device to sense the output. and then there will be also a feedback to the controller. So if adjustment is needed, a signal will be fed into the converter to adjust some values. Okay. Later, you will know what kind of values we can adjust to modify the output. Okay. And again here, I just want to mention once again for the conditions. Actually, from this condition, DC steady state, we should have already know the conditions. Okay, just because this one we just mentioned, right? So all the waveforms repeat every switching period. Okay, and this one important, not very important. Okay, so the duty ratio remains constant. So do you still remember what is duty ratio up to now? Okay, so in class exercise, we calculate the duty ratio. Do you still remember? We need to use one of the slides in topic 1. Okay, and okay, once again, the symbol of the duty ratio is D. Okay, in practical applications, D should change against time, right? It is because D can help to adjust or modify the output. But here, in this subject, D is a constant. Happy, right? So duty ratio is constant. Yeah, it means that so the switching times should also keep unchanged. Okay, so two conditions. So first one, switching waveforms repeats, okay, in cycles, and then second one, duty ratio remains constant. Okay, and we may take a break after 3.1. Okay. Okay, so now we try to look at the voltage and current of the inductor here associated with a switching power pole. So once again, this one is a switching power pole, okay, and then this is the input DC voltage, and output here we have a inductor. Okay, we have a inductor. Later you will know the purpose or why we put the inductor here. Okay, and then the waveform look like this. No worry now. Later we will know how they come. Okay. But anyhow, so every time we talk about or we learn about the inductor, we use very basic definition, right? This is the basic definition of the inductor voltage. So VL is equal to capital L DIL over dt. So this capital L is the inductance of the inductor, okay? And then DIL over dt. It is because here the IL, the inductor current, changes as time, right? Changes against time. So so we have the term DIL over dt, okay? And then we can do integration for both sides, and then rearrange the term. We will have the equation 3.1, okay? So and here we have the tau. Tau refers to the period. Refers to the period, okay? Okay, and then here it is because the tau is the whole period. And for the equation 3.2, actually we just extract the initial condition of the inductor current. The clever student may know why. At this moment, okay, may know why we extract the initial condition out of the integration. Okay, if you don't know why now, no worry, you will know that later. Okay. Yeah, so now equation 3.1 to 3.2. So actually we just extract the initial condition from the whole period here. Okay, so here means t is equal to 0. Okay, Okay, and now is the DC steady state. So it means that the initial condition should be equal to or identical to the final state, right? Okay, so that's why we have the equation 3.3. So actually, the equation 3.3 is the condition. It's the condition of the DC steady state. Final state is equal to initial state. Okay, so with this condition, so equation 3.2 should look like this, right? Okay, and then here the integration range is from 0 to switching period. 0 to switching period. So according to this waveform, no worry now, later you will know how it comes. Okay, but for this given waveform, okay, so actually one switching period can be divided into two. Actually, we also learned it or or saw that before, right? In topic one, the last line. Yeah, if I'm right. Okay, so we can divide the switching period into two time intervals. So one is off, the other one is one is on and the other one is off. Okay, so on is from 0 to dts, and t here is the duty ratio and times the switching interval. So here is the on interval, and then the second interval is from dts to ts. So here is the off interval, right? So here, this term can be expanded like this. Expand like this, and then it's equal to 0. Okay. So actually, here, just want to tell you, for this waveform, the average VL is equal to 0. Okay, so VL, capital VL is equal to 0. Actually, we just saw that before, right? So where is it? It's here, right? It's here. Okay, so uh, we just learned how it comes. Why VL, why the average voltage across the inductor is equal to 0. Okay, we just learned how it comes. Okay, so once again, we start from the basic definition of the inductor voltage. Actually, in this subject or in this topic, okay, every time we talk about um, the inductor, we'll start with the basic definition of the inductor voltage. Okay, and then for this one, integrate for both sides, and then we will have this equation 3.1, and then extract the initial condition out, and then we will have the equation 3.2. And it is because now the switching power pole is in DC steady state, so these two terms are identical. So it means that this one is equal to 0. It's equal to 0. So that's why we have this. And then for this one, this term, we can expand into two switching intervals. So the first one is on interval and the other one is off interval. And then the result is equal to 0. Okay, because we consider that in DC steady state. Okay, so up to now, is there any question? If you have question, you can ask. Okay, or if you have no question, you may go through example 3.1. Example 3.1. So example 3.1 here, we have the graph here, right? We have the waveform, and this is for the inductor current. The problem said that it is in DC steady state, and then with the inductor of 50 microhenry. Okay, and then the switching time period Ts is equal to 5 microseconds, and then ask you to calculate and draw inductor voltage waveform. Okay, so what is the inductor voltage waveform? This one. This one is the inductor voltage waveform. So actually you can copy. Okay, all you need to do is to calculate the voltage, peak to peak voltage. Okay, yeah. So try to think about that. If you have any question, feel free to ask, and then you try to think about this example, and if you don't want to do anything, you can take a rest. Okay, so we may take, now it's 9:38, 15 minutes. Okay, 15 minutes for you to have a break and also think of the solution for this example. Okay.